Hi, in this video, we're going to build a model of some common SerDes receiver equalizers using SerDesPy, which is a free Python library for SerDes simulation. We're going to be using these equalizers to equalize the waveform we generated in the previous tutorial, so I'd recommend you check out that previous video first. We're going to be using the receiver architecture shown in this block diagram. On the left, we can see the unequalized waveform that we generated in the previous tutorial. And this is going to be passed through a continuous time linear equalizer, or CTLE, a feed-forward equalizer, or FFE, and a decision feedback equalizer, or DFE. In reality, the FFE and DFE equalizers are digital, but we're going to keep the entire continuous time signal and apply equalization to each unit interval, so we can plot these kinds of eye diagrams after the FFE and DFE. Even though a continuous time signal like this doesn't actually exist in a real receiver, this kind of eye diagram plot helps us visualize the effects of the FFE and DFE. Now let's talk about how we're going to model the CTLE. Last time we used 100 gigabit per second PAM4 signaling, which means that the Nyquist frequency is at 25 gigahertz. The idea of the CTLE is to boost the signal around the Nyquist frequency and attenuate all the other frequencies. So we'd like our CTLE frequency response to look like this red line here, where we have 0 decibels of amplification or unity gain at DC. And then as we approach the Nyquist frequency, we get more and more gain. Here, we're amplifying the signal at 5 decibels at the Nyquist frequency, which is shown with this gray line. And then at higher frequencies, the signal is greatly attenuated. This kind of behavior can be achieved with a 1-0 two-pole transfer function. First, we put a 0 at lower frequency. The 0 frequency is shown with the green line here. And the effect of this 0 is that the slope of the frequency response increases by 20 decibels per decade. Then, at the Nyquist frequency, here it's shown with the blue line, we introduce two poles. And these two poles lower the slope of our frequency response by 40 decibels per decade, 20 decibels per decade for each pole. And so the effect is that it goes from up 20 decibels per decade to down 20 decibels per decade, creating this kind of peaking. This transfer function with 1, 0, and 2 poles can be implemented using the circuit shown on the bottom right, but I'm not going to get into how to pick component values to achieve this in this tutorial. In reality, a real 100 gigabit per second PAM4 SerDes would have a much more complicated CTLE circuit than this that would allow for us to have a programmable gain. That is, we could have this red transfer function, or if we needed less boost at the Nyquist frequency, we could change the frequency response of the CTLE to look something more like this. Or if we needed more boost, we could change it to look something like this. The advantage of this is that now we can set our CTLE to work with our specific channel that we're using. A channel with more attenuation will need higher boost, and the cost will be higher power consumption by the CTLE. We chose to use 5 decibels of peaking at the Nyquist frequency because this is a typical value for a real 100 gigabit application. So going back to our transfer function, we set omega z, the location of the 0 in radians per second, and omega p, the location of the pole in radians per second, to these values to achieve this red transfer function. We know our transfer function is going to look like this form, where we have s plus omega z in the numerator for our 0, and s plus omega p squared in the denominator for our 2 poles. And we also have this coefficient k. We're going to calculate k so that our DC gain is equal to 1. The way we do this is we set our transfer function magnitude, h of s, equal to 1, and we set s equal to 0 at DC, and we can quickly rearrange the equation to calculate that k needs to be 5.78 times 10 to the power of 11. Now we have our transfer function fully specified with omega z, omega p, and k. And the last thing we have to do is take it into standard form. Standard form for a transfer function is of the form where you have a polynomial in S in the numerator and another polynomial in S in the denominator. We call the coefficients of the numerator polynomial b0 and b1, and the denominator a0, a1, and a2. Now let's check out the code we're going to use to model the CTLE. First thing, we're going to import some packages that are going to be useful, including SerDesPy. Next, we're going to import some data that we generated in last tutorial, such as f, which is the frequency vector, h-pulse, which is the pulse response of the channel that we modeled, and signal, which is the channel's response to random data. Then we'll set up our samples per signal, which is 40 samples per UI that we used last time, as well as the data rate, 100 gigabits per second. Then we're going to set up our zero location, pole location, and coefficient k that we just calculated. And now we have everything needed to calculate the discrete frequency response of our CTLE. That's capital H CTLE, using SciPy's freaks function. This takes as argument b, which is the coefficients of our CTLE transfer function in standard form that we showed on the last slide, as well as a, the coefficients in the numerator, or in the denominator, and omega, which are the frequencies that our discrete transfer function is specified at. Now we can plot the Bode plot, see what it looks like. So here we have the same diagram that we showed on the slide. It has our 5 decibels peaking and our zero location shown in green and pole location shown in blue. However, we only have our CTLE response in the frequency domain, and we need to use the time domain to do our signal processing. So we're going to convert from the frequency domain into the time domain using the freq to impulse response function in SerDesPy, which essentially takes the inverse Fourier transform of the frequency response. So if we run this code and plot the resulting impulse response, which looks like this. Now, to see the effect of just the CTLE on the signal, first we can plot an eye diagram of our unequalized signal, then do a convolution between the signal and the CTLE's impulse response to get the equalized equalized signal, and then plot another eye diagram, see what it looks like. So this is the unequalized signal that we generated last time. And now we can see with the CTLE, it has much better eye opening. However, there's still some ISI that we could maybe equalize with the FFE and DFE equalizers. However, before we move on to the FFE and DFE, I'm just going to show you the effect of moving around the zero location to change the transfer function. So we were using this transfer function for our CTLE. However, if we want to have more gain at the Nyquist frequency, we can shift this green zero location back. And this means that we're going to have a longer upward slope time. And so the peaking is going to be higher. So let's just go from 5 times 10 to the power of 10 to 2 times 10 to the power of 10 for our zero location and see the effect. So now we have much higher peaking at 12 dB. And if we want, we can plot an eye diagram with this much higher peaking. And so this is what the eye diagram looks like with 12 dB of peaking. You'd expect it to be even greater, greater boost, but also with this high peaking, we get overshoot, and we'll take a look at that closer when we look at the next part of the code. But basically, you're getting way more ISI as well with this larger peaking. And so even though our signal is now at like plus minus 4 volts, whereas last time it was like only 1.5, obviously there's no usable I. So we're going to go back to our 5 decibels and use this for the rest of the code. Okay, now that we've fully specified the CTLE with its transfer function, it's time to move on to the FFE and DFE, which have tap coefficients that must be carefully selected in order to have the best equalization for a given channel and CTLE settings. In this tutorial, we're going to co-optimize the DFE and FFE tap coefficients with the adaptive least mean squares algorithm, and SerDes Pi has a function for doing that. So going to the code, the first thing that we need to do is to digitize our pulse response because the FFE and DFE are digital filters. So SerDes Pi has a function for doing this. It's called channel coefficients. And basically what it does is it takes the pulse response, it finds the main cursor by finding the maximum value of the pulse response. And then using the sampling ratio, it retrieves the values at a given number of UI before and after the main cursor. And so the number of UI before and after that we have to look at depends on how many precursor and postcursor taps we're using. So for an FFE, we're going to be using 2 precursor taps and 1 tap for the main cursor plus 4 taps post-cursor. So altogether, that makes 7 FFE taps and 2 DFE taps. So the most before the main cursor we're going to have to look is 2 UI, and the most after is 4 UI. So we're going to take a look at the channel coefficients, 2 UI before and up to 4 UI after. So first, we're plotting the channel coefficients of the unequalized channel. And as you can see, it has a main cursor that's about 0.35 and some post-cursor ISI. And then after our CTLE, the pulse response looks like this. So the main cursor has been boosted to 0.5 now, and a lot of the post-cursor ISI has been eliminated. In fact, there's even some overshoot that's caused by the CTLE. And you can see that we have some negative ISI for the first main cursor. Now, just as an aside, if you remember when we were doing like a much higher boost, we can take a look at what our channel coefficients look like then. So here you can see much higher boost. Yeah, we go all the way up to 1, but here we have a big post-cursor ISI term caused by the overshoot, and that's why the eye diagram looked so like the eyes were completely not open. Okay, so going back to our normal gain setting, we calculate the channel coefficients, and this is one of the things that we input to our adaptive LMS optimizer for the FFE and DFE tap weights. I'm not going to go into too much detail on how the LMS equalizer function works, which is what calculates the optimal tap weights. But if you're interested, you can right-click, go to definition, and take a look at the code and see what's going on. At a high level, what happens is we take a reference signal, which is like a perfect transmitter 4PAM eye diagram, and we try to get the DFE and FFE tap coefficients along with these channel coefficients to be as close to the reference signal as possible. And so we initialize our FFE and DFE tap weights as zeros, and then we do an iterative update process. And every time we get a little bit closer to achieving something that's close to the reference signal. And so all this code is just setting up things needed for this LMS equalizer function. But then we simply run the function in one step, and we come up with our optimal FFE and DFE tap coefficients. Now we want to plot some eye diagrams to see the effect of the FFE and DFE. We're going to use the class called receiver in SerDesPy to do this, which is just a helpful way of taking a look at a signal at the receiving end and applying different types of equalization to it, and allowing you to plot eye diagrams. So we're going to initialize our receiver class with our signal after the CTLE, as well as a few other parameters like the Nyquist frequency and sampling ratio and things like that. And then we're going to apply our FFE using our newly calculated optimal FFE tap weights, and then also the number of pre-taps, and plot an eye diagram. Then we're going to apply DFE equalization with our optimal DFE tap weights, and again plot an eye diagram and see what they look like. So this is the eye diagram with the CTLE and feed-forward equalizer. As you can see, the amount of post-cursor ISI has decreased since just the CTLE. And here we have an eye diagram with FFE and DFE, where there's basically zero ISI. So the eye opening looks really good, and our equalizers have done their job. Just to reiterate, this signal wouldn't actually be present in a physical transceiver because these FFE and DFE filters are digital, and so only the samples at the center of the eye would really be tracked. However, we're just taking the feedback and we're applying it to the entire unit interval. So we can see kind of the shape of what the eye would look like if there was like some jitter on either side. You could tell how big the eye opening would be. And because the DFE has one amount of feedback in one UI and then abruptly changes to another amount of feedback in the next UI, we can see this discontinuity here between eyes, but this isn't what a real continuous time signal would look like. Okay, so I hope that gave you an introduction on how you can model CTLE, FFE, and DFE equalizers using SerDesPy. There's a whole bunch more things that you can do to more accurately model a real transceiver, but hopefully this gets you started. Thanks so much for listening, and goodbye.